Sure. We are interested, I'm a biophysicist, and my group is a group of biophysicists, and we are interested in biological matter, in biological cells and tissues, and in particular, we use X-rays to look deep into a tissue. If you take a conventional, let's say, structural analysis, you take an optical microscope and just image a slide of your cell or your tissue, whereas X-rays allow us to go into something without cutting this down. And basically we want to understand how cells come together and how a structure in 3 dimensions is responsible for a certain function of some tissue, like brain tissue, muscle tissue. How is it all made up, and how does the structure explain the function? Now, if we do this, we're just talking about something that is static, that is a certain arrangement in space. But how about dynamics? Dynamics is also utterly important to see why things are and function how they do. And this is why we like to come to XFEL, because we have this incredible opportunity to image a scene in a controlled biological environment, in an aqueous environment, and to start a dynamics, for instance, by a laser pulse or by some other actuation. We use ultrasound, for example, and then we can film what is happening in that tissue on a wide range of length scales, from nanoseconds, picoseconds, even to microseconds, millions of a second, which is already pretty slow. Now, you would probably want to know, why is it important to observe things on a fast time scales, whereas we know that, let's say, cellular motion and even, let's say, assembly, how it builds, how the cell builds something, and that's all very slow. That's, like growth. But there are important things that happen on very fast time scales when, for example, you have a laser pulse that you use to do surgery on some tissue, like take cornea. A lot of patients get eye treatment using femtosecond lasers, where femtosecond lasers are used to, let's say, cut tissue and to create a controlled damage locally by that surgeon, because it's very precise. Now, if you focus an infrared laser pulse of a few femtoseconds or even picoseconds or nanoseconds onto some tissue, then hell breaks loose. In that small piece, you create a plasma, you destroy molecules, and you energize tissue at a small local spot, and that plasma that creates a tremendous increase in temperature and pressure, and then it expands. And if that energized matter expands, you create a small bubble. That's nothing like the bubbles that you know from mineral water that are more or less in equilibrium. It's highly out of equilibrium, and it creates a shock wave. And in this way, you can do things to tissue, and you can ask yourself, how is that response different from, let's say, if you do laser welding? If you have a material, probably you won't create a bubble like this. In aqueous environment or in tissues, that is tremendously different, and that's what we study here with XFEL radiation. So what we need is we need to have a small chamber of water and tissue. For instance, we will bring a cornea and also cornea implants that is typically a size of 8 millimeter in cross section, and have this in a chamber. And now we have to bring in the optical laser, and we have to have enough penetration power with the X-rays to go through that small chamber and let's say a path length of a few millimeter, at least up to a centimeter in water. So that means directly that we are talking high kilo electron volt energies, let's say 10 to 18 keV. That's the typical range of of X-ray photon energy that we're using. So that is provided at MID, and MID provides just the right kind of lasers that we need, and also an experimental environment where we can build up complex experiments. It's not in vacuum. We can bring in water. We can use ultra-fast optical cameras to, at the same time, simultaneously with the X-rays, see what do you see optically. All this is really a complicated experiment, and MID has the right characteristics in terms of radiation and instrumentation, and also flexibility. Well, what you want to do, you want to create and change a property in tissue. So you could, in principle, just do this by try and error. You bring in different laser pulses, and afterwards you inspect. Maybe if you just have an optical microscope, you already see, you might see a crater, you may see that there's something eroded. But it's very difficult to make this link to why is that going to happen, how does it happen, what are the stages, why is pulse length or pulse energy important, what is it actually doing? Because a tissue is soft and can react, and there's, let's say, a little earthquake, a shock wave moving, you want to see that, and you want to see that at high spatial and temporal resolution. You have to film and understand that. There are very subtle things and very complicated things of multiple bubbles expanding, collapsing. We started with just doing that in water, and we already saw things that people were not able to see before, because you shouldn't forget that with an optical camera you can look inside, but you have a lot of refraction. The optical light gets scattered by the bubbles in the interfaces, whereas X-rays have this property of being hardly not changed at all by matter. So we go through this and just pick up that scene undisturbed, and to see how that works really helps you to understand that better, and ultimately to fundamentally understand how strong laser pulses act on tissue or even water. We see tissue properties by going to extreme states. When does damage kick in? How about nonlinear optical effects? But then also for applications like laser surgery that will help to design, we hope that this type of research ultimately also leads to better tools. Yeah?